not quite be correct. So hopefully close enough. By way of introduction, Hadiseh came to Stanford in fall 2009 after getting her bachelor's degree and master's degree in electrical engineering from the University of Tehran. Probably I don't need to tell you that Hadiseh is incredibly smart, and I got a glimpse of her brilliance when we first met, and she brought me a box of chocolates. Hopefully after this, I'll be getting a lot of smart students coming to my office in the future. But more seriously, only later did I find out just how brilliant she was, not only by the accolades she had before coming into Stanford, just for some perspective, when she was enrolling into the University of Tehran, she had to take a placement exam that nearly 500,000 people take, and she was ranked in the top 225 people, so a pretty remarkable percentile. She was also second in her class at the University of Tehran. And then, while I'm not an electrical engineering professor, I understand that oftentimes just passing the EE-Qual exam is a pretty remarkable bar, and Hadiseh was ranked 7th on the EE qualifying exam. Her brilliance has definitely shown through in her research. It's been so much fun working with her. Oftentimes, I can just come up with some crazy idea, and it would probably take me weeks to work through the theory. Excuse me. So thankfully, I can just walk down to Hadiseh's office, and usually by the end of the day, she'll have some back-of-the-envelope calculations that tell me whether or not the idea really is crazy or if it's feasible and we should pursue it. In the course of her PhD, she's written 8 papers. There are a couple more that she submitted, a few more that are still sitting on my desk. So I feel like with Hadiseh, I'm pretty much the limiting factor in her own productivity. Also, just as I guess recognition of all of her work, she was recently awarded a graduate student award at the MRS conference that was held this spring. And then starting in September, she'll be accepting a postdoctoral position at the University of Bonn to work on quantum optics. So it's been a pleasure working with Hadiseh. Hopefully you'll enjoy her thesis defense, which is on metafluids and parity time symmetric metamaterials. Thanks, Hadiseh.
Thanks for the kind introduction, Judge. Good afternoon, everyone, and thank you for coming to this session. Today I'll be talking about new optical material phases that can be achieved in 2 generations of metamaterials, mainly metafluids and parity-time symmetric structures. 2015 has been announced as the year of light and light-based technologies by the UN, not only to acknowledge and appreciate the great advancement in the light science within the last millennium, but also to bring it to the attention of the public that how light is important and how it affects our daily basis lives. This is an interesting photo taken from International Space Station 240 miles away from our Earth, showing the light leading through the Earth, the tails of the stars and aurora, kind of combination of all the lights that surround us. But why light is important? We see the world through light, and in fact, if we change the manipulation of the light with the structure, we can see the world differently. That's an example of a typical green yellowish plant that you can see everywhere with textureless green leaf. But if you look at the leaf under polarized microscopy, you can see the interesting features of this structure. Light also become useful in knowing our biology and our brains and bodies. Thanks to the fluorescence microscopy, now we can see the interesting images of the astrocyte and cells that are abundant in our brain with spinal cord and get an understanding about our biological systems. But light is not only limited for seeing the world and discovery, it also initiated and motivates lots of technologies. Nobody can deny the importance and influential effect of optical fibers in revolutionizing our telecommunication era. Thanks to these communication channels as a secure and wideband channel, now we are able to send 1 terabyte data per second over 7,000 kilometers for intercontinental telecommunication. Light also can be transformed to other forms of energy. For example, the solar cells can capture the abundant amount of the solar light and transform it to electricity, make it to a form of energy which is useful for, make the space journeys possible and useful for our space stations. Lasers are also important in lots of technological, medical, and biological applications, and especially short wavelength lasers, drastically changed the data storage and made high data storage is possible. As you might know, the Nobel Prize of 2014 has been awarded to blue LEDs as a kind of efficient and environmentally friendly source, just to acknowledge and appreciate the importance of these sources better. All of these phenomena, however, happen because of the interaction of the light with natural materials. However, as usual, nature imposes some restriction on us. Most of the natural materials, or all of them, have positive refractive index. You are very well familiar with this ray tracing picture. In a prism and by positive refractive index, I mean that the incident and refractive beam are on the opposite side of the normal one. Or the picture of a broken straw in your glass of water shows that how light is refracted in these two different media. Excluding some cases like nonlinearity or magnetic materials, most of natural materials are also non-directional. So if you have a waveguide, it typically doesn't matter if the wave propagates forward or backward. So these restrictions on natural materials have initiated lots of research and indeed was the motivation of my thesis as well. In this presentation, I'll be talking about two main trends of our research, mainly metal fluid that addresses the positive refractive index of light and made a platform for a tunable negative refractive index material and a new generation of optical systems which is called peri-time symmetry, which shows high directional properties. Let's start with metal fluid. As the name implies, that's a metal material in the fluidic phase. But what is metal material? So as discussed, all of the natural materials have positive refractive index related to the permittivity and permeability of this structure. But nothing can abandon our imagination thinking about materials with having negative permittivity or permeability. And in fact, the idea has been around from 1960 when Veselago hypothesized materials with negative permeability and permittivity and predicted some exotic phenomena in this system. The idea is simple, replacing the atomic constituents with some synthetic constituents that can provide the property that we are looking after. Thanks to the growth of the fabrication, now we have different generations of metal materials that can span the whole range of electromagnetic spectrum. That's an example where the parallel wires, the arrays of parallel gold wires has been used in microwave range of frequency to get materials with negative refractive index. A recent study from our group shows that if the constituents are replaced by crescent-shaped materials, we can get a negative refractive index in the visible over a broad range of frequency. And another recent work shows that alternating layers of the metal and dielectric can be used to get negative refractive index in the ultraviolet. But as you notice, most of these materials are in solid state, and they require design top-down fabrication with a small particle. So we were thinking if we can take advantage from bottom-up assembly, of colloidal assembly to get gram-scale materials with large particles. Just to put more emphasis, the missing ingredient or the key point is optical magnetism, because as you know, in the optical range of frequency, we have metals with negative permittivity. So we are looking after a material or a system that can provide us with tunable permeability. And now if we have an optical magnetism, now we can have a fancy fluid that the broken straw seems reverse. Or we can do more fundamental study. For example, we can change the radiation properties of the material. That's the transition of the europium ion, where the D to F transition is accompanied with both electric and magnetic type transitions. And now if we have a magnetic material in the vicinity of this structure, we can selectively control and tune the radiation corresponding to the magnetic part. But how we can get optical magnetism? Going back to our intuition, the magnetic dipole is associated with a circulating current. And our idea, inspired by the work of Professor Fan from Harvard University, when they first colloidally synthesized a system of trimer partial particle that shows magnetic permeability or resonance when the electric field is polarized in the plane. To characterize the feature of this structure using a dark field microscopy, that's how actually the scattering from this system looked like. You notice that there is substantial difference if the incident light is polarized along P or S direction. In fact, S-polarized scattering is accompanied by a large shoulder at low energies. Since we have lots of metallic constituents in a system, the electric dipole obscures the scattering property of the system. Using a cross polarizer, we can cut the contribution from the electric dipole, and now you'll see that shoulder now evolves to be a significant peak. To see the behavior of the peak or the nature of the peak, if we now look at the displacement current in the system, you see that it's associated with the circulation, which is the hallmark of the magnetic moment in the system. But as you notice, the system is planar and it's polarization sensitive. So we were asking ourselves if we can make a three-dimensional system with polarization insensitivity. So that's the system that we are proposing. And a cluster of metallic nanoparticles and a dielectric core. So thinking about that fancy liquid, that's how actually the ingredient of this liquid looks like. And to show you that these indeed support magnetic resonance, that's the displacement current in this system, and you see that it's accompanied by a circulation. And if you look at the scattered magnetic field of the system, you notice that this is 15 times larger than the magnetic field scattered in free space. So the system indeed supports magnetic resonance. But how we can synthesize or make the system? For that we use protein-directed assembly when we have the polygonally synthesized silver nanoparticles functionalized with ligand biotin and polystyrene beads functionalized with streptavidin. Since they are conjugate polymers, they stick together when they are in a solution. So that's how the ingredient of the system and the final product look like. So looking at the final assembled system in transmission electron microscopy, you notice that we have a bundle of these metallic particles surrounding a core. And in scattering electron microscopy, you see the three-dimensional behavior better. To get a better understanding about the three-dimensional nature of the system, this is the TM tilt series. From this structure shows that how a polystyrene bead is surrounded with metallic nanoparticles. But what's the resonance frequency of the system, or what are the spectral properties of the system? For that, we utilize the generalized multiple method accompanied with finite difference time domain analysis. And that's how the scattering from our system looks like. It's accompanied with two resonances. But since we have lots of metallic constituents in a system, lots of the radiation comes or scattering comes from the electric dipole. To suppress that part, we also measure the directional scattering, which is the scattering from the system in a direction of the electric field. And we notice that now we have two dominant peaks, and it actually shows us that indeed we have non-electric dipole contribution in a system. To measure it, we made a flow cell out of two glass cover slips and flow this metafluidic between the cover slips. The structure is illuminated with a light coming from the condenser, and the scattered light is collected from with an objective in a dark field transmission setup. So if we capture and collect all the light, which we call it unpolarized, again you notice that we have a shoulder at low energies. This shoulder comes because of the fact that we have lots of scattering because of the electric dipole in the system. So if we now look across polarizer, you notice that this shoulder evolves to be an independent peak in a system. So this study tells us that we indeed have non-electric dipole contribution in the system. But what's their nature? So now if we decompose the field scattered by these metal molecules in terms of spherical harmonics, and the fields radiated by electric dipole and magnetic dipole, that's what we get. So the total scattering spectra can be decomposed as a summation of electric dipole contribution and the magnetic dipole contribution. And you notice that while the electric dipole is broadband, the magnetic dipole is pretty sensitive and localized between 600 and 700 nanometers. So then we were curious at how we can separate these phenomena and features better in our measurement. And it seems that a system with polarization and angle resolved of that metal fluid. Now, if you put a linear polarizer in front of the laser beam in such a way that we have electric field along the x direction and magnetic field along the y direction, now in a plane normal to the direction of the laser beam, that's how the radiation of the electric dipole and magnetic dipole look like. Moreover, the field radiated by electric dipole is in the plane or transverse, while the field radiated by the magnetic dipole is out of plane and longitudinal. So now if we have a detector that measures this radiation pattern for different angles of phi and for two different orientation of polarization, we should be able to separate the contribution from the electric dipole and magnetic dipole. And indeed that's what our measurement appears to be. So we have a sinusoidal square type variation which corroborates properly with the radiation of the electric dipole, and we have a cosine squared variation like the radiation of a magnetic dipole. If we compare these one with a control sample, which is a combination of a silver nanoparticle and polystyrene, you notice that there is significance between the magnetic dipole scattered by this ensemble and the one from the control sample. To give you an estimate about the strength of these dipoles, it appears that the magnetic dipole is 12% of the electric dipole in a system. So we indeed have simultaneous amount of the electric dipole and magnetic dipole in the system with some comparable value, or at least the same order. Then we were curious that what is actually the property of the final product and the metal fluid, or how we can tune the properties. So since we have the polarizability of every individual metal molecule, we can use a homogenization technique like Clausius-Mossadi or Maxwell-Garnett to calculate the effective properties of a system. And here I'm showing the real part of effective permeability and refractive index as a function of wavelength and filling factor. And you notice that indeed the values are tunable in a broad range of values. And you notice that the sign can change whenever there is a resonance in a magnetic field. To give you a better estimate about the values, I'm comparing the permeability and refractive index for two low and high concentration. When the concentration of the metal molecule is less, about 10%, you notice that the resonance feature of the permeability and effective refractive index is pretty small, and they are barely deviate from the value of 1. But if the concentration increases to a filling factor like 50%, then the resonance increases, and now we have a region that the effective permeability and refractive index both dip below 0. So with that, I will conclude the first part of the talk. Here we talked about a system of self-assembled clusters of metallic and dielectric nanoparticles that can have simultaneous electric and magnetic dipole in the visible range of frequency. We used dark spectroscopy accompanied with angle result and polarization result type measurement to verify the presence of both in our system. And finally, we showed that how the properties of the system are tunable as a function of filling factor and frequency. Specifically, when we increase the filling factor, we can have the regions with negative permeability and negative refractive index. So, from the time that they were introduced, metamaterial suffers from loss. Our system is not an exception as well. So, thinking about a way to overcome the loss, the immediate answer would be using the optical gain. And in fact, that's the answer. The optical gain has been used a lot to overcome the loss, to amplify the signal, or even get the lasing in the system. But thinking about all the devices that we have so far, like silicon devices, or grating, or photonic crystal, all of them take advantage of manipulation of the real part of the refractive index. So thinking about the gain as a new knob, we were asking that question, that if the gain can be utilized as another knob or a new knob in a system, that by manipulating its spatial distribution, we can get new phenomena or new optical properties. And that takes me to the second part of the talk, which is about a new generation of metamaterials called Perry-time symmetry. And they are the system which utilize the judicious amount of the gain and loss toward new optical phenomena. Let me briefly introduce you the notion of PT symmetry. A potential is PT symmetric if that's conserved under parity and time reversal symmetry. To remind you, that's how these operators act on the space or position space or momentum space. So more specifically, a potential is PT symmetric if Vx equals V minus F conjugate. Thinking about the potential, optical potentials and its relation to the permittivity, then it means that a PT symmetric optical system has the permittivity that satisfies these two conditions. So in a nutshell, PT symmetric deals with symmetric structures that have balanced amount of the gain and loss. The idea has been around from 2009, and by utilizing this simple notion in different devices, people have been able to demonstrate new and exotic optical phenomena. For example, a recent report shows that if we have the coupled ring resonators with balanced amount of the gain and loss, then we can get stable single line lasing in this system, which is not only spectrally confined but also is spatially confined. Moreover, since that's a robust single line laser, one should be able to increase the power of the laser at will without coupling the power to other modes of the system. And our recent work, again related to the laser, utilizes this idea in ring resonators. A lot of people in the audience know ring resonators have been interesting because of the large clogging factor. However, they support lots of whispering gallery mode. So most of the time, it's hard to get single mode lasing in such systems. In this work, it's been shown that if the periphery of this resonator is decorated with alternating layers of the loss and the gain, one should be able to couple power selectively to a node of the system and get a robust single lasing in such system. To show you the property of the system, let me briefly explain one example that clarifies some general aspects of the system. Assume that we have two coupled disks. Because of the coupling between these two structures, the resonant mode of the total system would split. However, if we have or doped one of the systems with a gain and one of the systems with loss, and the value of the gain and loss are given by this kappa value, then that's what we get as a function of the detuning or the mode of the system as a function of the value of the gain and loss in the system. You notice that there is a threshold before which we have two resonant modes in a system, and after that threshold we only have one resonant mode in the system. So it seems that we have two different phases which are separated by a point or a boundary which is called exceptional point. In a geometry like add-drop filter, now if we look at the drop line or the output, when we are in the first phase corresponding to these points or this value of the kappa, you notice that at the output we have two resonant lines corresponding with two resonant nodes that we have in the system. However, passing that point, you notice that we only have one resonant line and detuning is 0. So it resonates at a frequency as if there is just a single disk in a system. No matter how complicated these devices are, the general theme of the PT symmetric optical devices is the presence of the phase transition and the appearance of the exceptional point. Our study on PT symmetric realms investigate the effect or the implication of these type of symmetry in nanoscale systems, and we propose two different types of materials. One that makes a good candidate or platform for lossless SLR lensing, and then utilizing these materials, one should be able to control the emission of the dipole, and it suggests a platform for identification of chiral enantiomers. Let's start with a simple planar case. We have a metal insulator metal waveguide, and let's, for sake of simplicity, only focus on the TM mode of the system with magnetic field out of plane and electric field in the XZ plane. Since the structure is symmetric, the modes of the system have definite parities. And also along this line, which is called surface resonance frequency, the parity of the mode switches. So we had even mode below surface resonance frequency, and we have odd mode above surface resonance frequency. Now, if we put two of these waveguides together toward making a 5-layer structure, and now having the same refractive index in both channels, but allowing that the imaginary required the refractive index changes with the same amount, and simultaneously, now we can have a PT symmetric structure as the criteria suggests. But starting from the passive case, when kappa equals 0, because of the coupling between two waveguides, the mode split. And that's why we have two modes below and two modes above surface resonance frequency. How these modes look like? At a particular wavelength like 1165 nanometer, if you look at the cross-section and the magnetic field of V1, you notice that we have an odd distribution of the magnetic field with respect to the YZ plane. However, since the mode below surface resonance frequency are even, you notice that in each dielectric channels, the magnetic field is distributed evenly. Going to the other mode, which is V2, now you notice that the distribution with respect to YZ is even. And again, you notice that the distribution in each dielectric channel is even as well. However, no matter what's the parity of the magnetic field in these two cases, the power with PZ, which is the power propagates along the Z direction, is always equally distributed in the top and bottom channels. Now let's increase the value of the gain and loss in the system by virtue of changing the value kappa. What happens? Now we have two counteracting mechanisms. We have the coupling that splits the mode, and we have the gain-loss perturbation that merges the mode. So then there appears to be a condition or a point that the mode coalesce, and as we discussed it briefly, that's what's called the exceptional point. But what's the notion or the implication of the exceptional point in our system? Going back to the same wavelength, now if we look at the distribution of the magnetic field for V1 and V2, you notice that none of these modes hold their parities. In fact, they lose their parities and they are skewed. But now if we go back and look at the distribution of the power, you notice that for both cases, the power is still evenly distributed in the gain and loss waveguides. If we pass the exceptional point, however, now neither the distribution of the modes nor the power hold their symmetry. And in fact, now we have the modes which are exclusively gain mode, which most of the power is in the gain channel, and we have exclusively loss mode, which most of the power is in the loss channel. But how we can interpret or understand this system better, or that kind of interaction between the coupling and gain-loss perturbation? For that, we utilize perturbative analysis. And since we were going to use some sort of analysis like Rayleigh-Schrödinger perturbation, we formulated our eigenequation for the modes of the system in terms of time-dependent Schrödinger equation. So if you are looking after the wave-guiding modes of the system, which varies exponentially along the Z direction, these spatial derivatives can be replaced with a constant like kz. Now we end up having a generalized eigenvalue equation for wave-guiding modes of the system. The Hamiltonian H hat is a function of geometry and material properties of a system. Now let's break the PT symmetric system in two parts. One part, which is the symmetric waveguide, where we have the alternating layers of the metal and dielectric without any gain and loss in the system. And the other one that we have the amount of the gain and loss as a perturbation. Since our original system is symmetric, as we discussed, the modes have definite parities. So if we use the first order perturbation, then we notice that since this perturbation is anti-symmetric and the modes have definite parity, this always vanish. But going to the second order perturbation, you find the formula or the behavior which is very similar from what we expect from second order perturbation, with a subtle difference, the presence of this minus sign. In fact, this minus sign has the main implication of the coalescence of the state because it decreases the level between the eigenstates and leads to the coalescence of the modes. Now, if we use this kind of analysis, for the modes of the system below surface resonance frequency for V1 and V2, now we notice that for different values of the gain and loss, we have these behaviors, and for all of the cases, you notice that we have the values that the propagation constant becomes the same. And indeed, these points are exceptional points. If we compare this one with the exact analysis, you notice that the exact analysis and second order perturbation match pretty well, especially for small values of the perturbation or amount of the gain or loss. So this analysis analysis gives us a good understanding about the implication of the coupling and gain loss perturbation in our system. But that's a 2D system, so we were curious how we can make it three-dimensional or utilize these directionality properties in nanoscale systems toward making a directional material. So the answer is by stacking them. In fact, the stacked layers of the metal and dielectric has been used a lot in the past for different applications. The one that we were particularly interested about is about flat lensing. So these, the alternating layers of the silver and titanium oxide in the past has been used to make a flat lens which can overcome the Rayleigh diffraction of optical microscopy. However, this structure suffers from two problems. It has large reflection loss and it has large insertion loss. Toward making an ideal device, we need to decrease the reflection loss to 0 and increase the transmission to unity. Our study shows that a PT symmetric metamaterial like this can do the job, and we can make an ideal vessel-level lens. But let's investigate the property of the system. These graphs show the variation of the wave vector along the waveguide or x direction as a function of energy and the modes in the first filament zone. Similar to what we have for the waveguide, now instead of the modes we have bands of energy. Similar to the waveguide case, we have B1 to B4. And as we increase the value of the kappa or the gain of loss in the channels, you notice that similar to what we had for just one unit cell of this structure or the waveguide, now we have the exceptional point that the modes coalesce together at that point. But what's the implication of the exceptional point on this three-dimensional structure? The good way to looking at is investigating the equifrequency contours, which are just a cross-section of these band diagram at a fixed energy for a function of kx as a function of kz. When kappa equals 0, the mode of the system or the bands of the system can be categorized to two parts, the hyperbolic one and the elliptical bands, which comes because of the equation that this band satisfies in kx, kz plane. By increasing the value of the gain and loss, or the kappa in the system, you notice that we can change the curvature of the bands. And if we increase that value of the gain and loss further, we can drastically change the behavior of the band, for example, from a circular to an elliptical, or even change the entity of the bands, for example, being from a hyperbolic to an elliptic. So by tuning the value of the gain and loss as a knob, we can control the effective behavior of this material. But this material also has some very interesting resonance features. So for the particular wavelength of 445 nanometer, which corresponds to the elliptical bands of the system suitable for lensing, that's the exception. That's what we found as the exceptional point of the system. Now, if we illuminate the system with a plane wave from the loss side at the angle of 45 degrees, the reflection from this structure diminishes to 0. However, the transmission increases to unity. So in spite of all of these downs and ups that we have in different layers of the structure, finally the transmission appears to be unity at the output. And more interestingly, by following the direction of the pointing vector in the material, the effective refractive index appeared to be -0.7. So indeed, this structure is a platform for vessel-level lensing. It has zero reflection, unity transmission, and it has negative refractive index. But as you notice, there is no plane of symmetry in this structure, especially in the XY plane. So we were curious at how directional this structure is, because as we discussed before, that's one of the properties of the PT symmetric devices. Now, if we change the direction of illumination from the loss side to the gain side, you notice that the scattering property changes drastically. Mainly, the reflection coefficient increases to 2, which means that some of the power, as you see, propagates toward the source. However, the transmission is still unity. Although the layout of the power propagating along this direction varies drastically, we still get unity power at the transmission. And again, looking at the effective refractive index of the material in the system, we find that the refractive index of this material is around -1. So this structure is not only a platform for vessel-level lensing, it has the interesting property of being directional. And if we looked from the loss side or gain side, we different properties from the system. So we were interested to investigate the scattering properties of the system further. So for the particular wavelength and angle that I showed you, here is how actually the reflection from the loss or gain varies as a function of gain-loss parameter. So 1 unit cell, you notice that the reflection from the loss side or gain side has some resonance condition and diminishes to 0 at particular values of the cathode. If we increase the number of unit cells to, let's say, up to 15, although there is drastic change in the scattering parameters of the system, the condition of 0 loss, 0 reflection remains the same independent of number of unit cells. Looking at the transmission, however, you notice that whenever we have a condition of 0 reflection, the transmission increases to unity. The same phenomena happens when we have 0 reflection from the loss side and unity transmission from the material. So it made us thinking that there should be a new type of power conservation law in the system. By investigating the property of the scattering matrix of the system, we found that they have an interesting symmetry. And in fact, that's what we found as a kind of generalized power conservation law dominating the behavior of the reflection and transmission from the system. And now you can see that whenever reflection vanishes from one side, the transmission increases to unity. That's what's called as a kind of resonance condition in a system and make it a good platform for perfect Veselago lensing. However, so far we only considered the behavior of this material as a directional bulk of material for propagating plane waves. We were interested to investigate the structure further for evanescent component as well. But why it's important? Because it helps us to understand that how actually this metamaterial can control the dipolar emission. Considering our prototype structure, a planar structure like this with translational invariant in the x and y plane, the field emanated by this dipole can be decomposed to infinitely many plane waves. So for sake of simplicity, I just dump everything as a function of fx, but the main notion is that the plane waves emanated from these dipoles, their momentum in the xy plane varies from 0 to infinity, and each plane wave is weighted with an exponential term which is related to the separation of the dipole from the structure. Now, if you look at each integral and split it into 2 parts, which they have different behaviors, we have one part with where the in-plane momentum varies from 0 to k naught, which means that the emanated plane wave is propagating. And the other part, which is k naught up to infinity, tells us that the emanated wave from these dipoles are evanescent. The first part we just investigated. That's how we generalize and derive these kind of generalized power conservation law. But what about the evanescent component? Our study on the scattering properties of the system shows that the evanescent reflection from these structures satisfies the condition that Rg equals Rl conjugate. So in the rest of the talk, I'll be talking about the notion or the implication of this symmetry and the effect of the exceptional point on the power emitted from the dipole. Let's start from the passive case when we have cathode pole 0 in a system. And since the structure is translationally invariant, we have TE modes and TM modes as individual and independent solutions of the system. For a vertical electric dipole which exclusively couples to the magnetic field or magnetic mode, TM modes of the system, that's how the layout of the normalized power looks like. For the other direction, which is the horizontal electric dipole, you notice that the behavior is pretty similar, except some difference in the value of the emitted power. But the main points that we're interested about is that the power emitted from the dipoles peaks whenever there is large density of optical states in the modes of the system. Also, away from these peaks, the power drastically decreases. So, if we, for example, consider a low energy range like this, we don't have any resonant TM mode in a system, and we are far away from the resonances. Why that matters? Because we are interested to investigate the property of the system away from its natural resonances. The study cannot be completed without looking at the TE modes. By virtue of duality, a vertical magnetic dipole only couples to the TE modes of the system, and you notice that the peaks of this power corroborates properly well where we have the cutoff frequency of the TE modes. The horizontal case of the magnetic dipole, which couples to both TE and TM modes, has the signature of the TM mode as well. And again, if we zoom in at the low energy part of this diagram, you notice that we don't have any TE mode. So let's choose an energy from this low energy part and investigate how the system behavior changes by changing the value of the gain or loss. For a low energy like 1.2 electron volt, since we do not have any TE mode in the system, I'm showing the variation of the reflection coefficient for TM mode as a function of in-plane momentum and gain loss value. So you notice that this diagram has some general features. The reflection coefficient has some signature of the modes of the system. Also, you notice that by changing the value of the kappa, we can control the wave vectors of the mode as we discussed before. And also, you notice that there is a threshold at which it seems that we only have one mode, and the modes coalesce. And indeed, this point is the exceptional point that we introduced before. But what's the notion of the exceptional point, or what's the effect of the exceptional point on the power emitted from the dipole? So, going back to the condition for the 1.2 electron volt and the dipoles 20 nanometer away from the structure, if we calculate the power emitted from these dipoles, the horizontal and vertical electric dipole, you notice that the power increases by orders of magnitude at the exceptional point. For the magnetic dipole case, when we have vertical magnetic dipole which does not excite the TM mode, you notice that the power is exclusively negative. But however, when we go to the case of the horizontal magnetic dipole, which couples to the TM modes of the system, you notice that again the power peaks at this exceptional point. So it seems that a new resonance feature appears because of this exceptional point. And it can increase the amount of the power by orders of magnitude. So then we were asking the question that if we can utilize this large density of optical states to tune the radiation properties of more complicated sources, because as we discussed, that's some property of the structure and it's not related to the property of the source. So the particular sources that we were interested about were chiral enantiomers. To briefly introduce you, chiral enantiomers are mirror image pair of each other, and their electronic properties are associated with simultaneous radiation of the electric dipole and magnetic dipole. But why they are important? In lots of chemical synthesis concerning making these chiral molecules, the output or the final product is not a pure enantiomer. In fact, they appeared as a racemic mixture. But for lots of biological and medical applications, we require pure enantiomers. Since these entities or enantiomers have the same physical and electronic properties, it's hard to separate them. Currently, there are some techniques based on the by virtue of interacting them with another chiral entity or some chemical method just to separate them. But they are not efficient, and most of the time they are very molecule specific. So we were thinking about another scheme, and we found out that if we can change the power emitted by these chiral enantiomers selectively, we should be able to identify them first, and then using another technique like photoablation or photoionization, we should be able to later separate them. So then we were curious to see that if a PT symmetric structure like this with large LDOS can actually help us to discern the power emitted by these dipoles. So going back to the same small value of the energy and 20 nanometer separation from the structure for a pair of electric and magnetic dipole in the XY plane, that's what we get for the difference between the power emitted by these enantiomers. You notice that for all the separated angle, the angle of separation between these dipoles, the power increases at the exceptional point. And although it's angle dependent, whenever the angle is something different from zero, you notice that there is no visible difference between the power. But more interesting with the separation between the power peaks at 91 degrees, which indeed is the angle between the electric and magnetic dipole in the natural chiral molecule. And at that point, we can increase the difference between the powers by 4 times. So indeed, this actually is an interesting non-chiral platform to identify chiral enantiomers by selectively changing the difference between the power emitted by chiral entities. But please remember that these structures were chiral. From the beginning, we talked about the directionality of these PT symmetric structures for propagating platelets. Then we were asking that what's the notion of directionality in the power emitted by these systems? And then going back and looking at the symmetry that I had for the reflection from the gain and reflection from the loss, then you notice that if we change the sign of the reflection or change it to the complex conjugate, you should be able to change the sign of the power emitted by that part. And if the evanescent component contribution is dominant, one should be able to change the sign of the whole power. So it means that by toggling the location of the dipole from the loss side to the gain side, one should be able to tune the sign of the power, which means that depending on the location of the dipole, it could be either emitting the power or absorbing the power. As a final note, I just want to put more emphasis on the effect of the evanescent component. Since it's related to, it's also weighted with an exponential term, it's very delicate and sensitive phenomena regarding the separation of the dipole from the structure. So if you have a dipole on the left side, by taking the dipole farther and farther away from the structure, you notice that this power is exclusively positive. However, from the gain side, you notice that the power first becomes positive, and then no matter the dipole is close to the gain or loss side, both approaches 1 as if there is no scatter in the vicinity of the dipole. So it means that not only by toggling the location of the dipole from gain to loss, also by changing its separation, one can change the behavior of the dipole. With that, I want to conclude the second part of this talk, where I introduced the concept of PT symmetric in optics and plasmonic systems. Here I talked about 3 main systems. The PT symmetric waveguides show an abrupt phase transition close to the exceptional point and made a platform for directional nanophotonics. We talked about PT symmetric metamaterials, where they're highly directional, they have zero reflection, unity transmission, and they were interesting platform for vesicological lensing. We also talked about the capability of these PT symmetric optical potentials to control not only the magnitude but also sign of the power. And finally, we introduced that how they can be used as an efficient platform for optical identification of chiral enantiomers, and finally sorting them. So this takes me to the concluding slide of this presentation. In this talk, I addressed 2 main limitations of natural materials, mainly having the positive refractive index, where we introduced the protein-directed assembly of the dielectric and metallic nanoparticles to make isotropic and gram-scale metamaterials that its refractive index can be highly tunable. We also addressed the non-directional properties of the natural material, and for that we introduced the concept of PT symmetry and designed PT symmetric metamaterials where they were highly directional and they can show exotic features like resonance condition that we talked of zero reflection and unity transmission and make a perfect vesicological one. We also talked about the capability of these metamaterials for controlling the dipolar emission, both in sign and magnitude, and more importantly as a kind of non-chiral platform for identification and separation of chiral enantiomers. With that, I want to conclude the scientific part of my talk, but before concluding the talk, I want to take a couple of your minutes to acknowledge and appreciate people that helped me within the last 6 years. First, I want to thank my advisor, Jen. This is the couple of photos of Jen that I really like. I met Jen in December 2009 when she was a describing her thesis work and introducing me the idea of coping. And she was so passionate and enthusiastic that I said that I would be invisible in my defense session. But down the road, my interest got changed. I was more interested in new ideas and new directions in optics, and I wanted to explore it. I really want to thank you and appreciate you for giving me the opportunity to learn new things, and at the same time, be a great mentor and advisor to guide me in the right direction. Not only being my academic advisor, I want to appreciate you to be a great friend and a willing person to help. Thank you. Second, I want to thank my committee members, Professor Vučković. I always was inspired by your dedication and in your enthusiasm in the classroom. I also was honored to be co-advised with you. Thanks for specifying the time, for just having a meeting with me and answering my questions. Most of the things I remember, I asked Professor Vučković to ask for a meeting, and I rushed to her office and started talking very fast, and she was so patient, just listening to my questions and trying to give me the best advice possible. I also want to thank you for supporting lots of my application in the fall corner and also giving me very insightful and beneficial advice for deciding properly. Thank you. I want to thank Professor Miller. I enjoyed attending your quantum classes, and also I had the pleasure of TAing your engineering physics course. That was a great opportunity interacting with hundreds of freshmen engineering students from different disciplines. I also want to thank you for great scientific discussions we had about the course, about when I was TAing your course, and later about my project. Again, I also want to thank you for supporting my application. Specifically, I remember that I got a notification that you supported a letter of recommendation for me on Christmas Eve, which was so. Professor Brandersman, thank you for attending the session. I also benefited from your class, and in addition to that, lots of symposia and great board and research conferences that you organized. Also, thank you for being a great scientific neighbor, allowing me just to sneak through your lab and using your FAR setup for different projects. Thank you. And Professor Hall, thank you for accepting to be the chair of the committee and specifying your time to attend this talk. Your names, in my mind, is linked with a great and nice person, which as the last examiner of my E-calls, he actually made that day a memorable day for me. Thank you. Third, I want to thank my friends in D-Lab. Around 157 and people around were really my home and family in the last 5 years. We started this, probably I'm among a few people that share this photo because we were just a couple of people started the lab in 2010. Then we grow, and that's how the lab looked like 2 years later. And now that's our group with lots of great, inspired, and motivated people, and also just including 2 great alumni of our group and the first generation of our alumni. I want to thank you not because I learned a lot from your scientific vision and lots of the things that you taught me, but specifically I want to appreciate that you, in practice, you taught me the value of friendship, support, and caring. All you are great people, and I wish for each and every one of you the best possible in your life, in your career. Thank you. Friends and family, I barely can find the time that describe and express my feeling and my deep gratitude toward all the great that I had, all the great friends that I had during my time here at Stanford. That's the photo of us we took about 2 years ago, someplace near Zion. If you cannot spot me, I'm just a little person. And literally, that's the feeling that I have whenever I'm among you. I feel I'm embraced with your love, support, and caring. And I feel very grateful and blessed for having you around. Unfortunately, at the time of this photo, a couple of our great friends were not around, which I want to particularly thank them. Layla, Nargis, Tahir, and Humaira, they were great people that they helped me literally from the first time that I arrived here at Stanford. Thank you. I also want to thank my parents. I haven't met them for a while, but I always feel the karma and the great and positive energy and support that they are providing me with. I want to thank them for having trust in me, believing in me, and supporting all of my ambitions and decisions. My parents-in-law, the great and nice people that I was honored to interact with them within the last couple of years. And finally, my brothers Reza and Javad, which are the joy of my life. And literally, they try to keep me feeling that I'm among them and with them by sending me lots of photos and selfies from themselves whenever they are in a cafe or in front of an elevator. And last but not least, I want to thank Sam, who I'm really honored to share my life with him within the last 3 years of my life here at Stanford. He's a photo of Sam before we met each other, but it appeared to be his common gesture whenever I tried to be very profound or saying something so philosophical or rational. Thanks for keeping that gesture and reminding me how far I need to improve myself. Your abundant amount of life, love, support, caring, tolerance, and patience make me responsible not to be a good person, but making the world around me a better place for others to live. Thank you. With that, I will go back to my conclusion slide. Thank you all for your attention and specifying your time.